Okay, so now we're going to be moving on to Unit 6, Simple Harmonic Motion. This is a much smaller unit, so there's not going to be too much for this unit, but it's still important to know. So we're going to move on. Next slide, please. All right, simple harmonic motion. So simple harmonic motion is the motion consisting of regular, period, back and forth oscillations. Acceleration is always in opposite direction from displacement. So a graph of displacement versus time will result in the trigonometric function sine or cosine. So types of simple harmonic motion are springs, pendulums, waves, and uniform circular motion. Next slide, please. So the kinematics of simple harmonic motion, they are based on the sine or the cosine functions, which relate the displacement, velocity, and acceleration of the object to time. So this is a really big, important equation to remember, which is T equals 1 over F, or the reciprocal of it is going to be F equals 1 over T. So the period of the motion is related to the frequency of the motion by the equation like we just talked about, T equals 1 over F. So T is going to be the period and F is going to be the frequency, and the frequency is going to be measured in hertz. So the position is going the equation for position is going to be x of t equals a cosine. And then for velocity, it's just going to be the derivative of that. And then acceleration is going to be negative w squared a cosine. All right, next slide, please. All right. So for spring force, it's going to be measured by negative kx, and this is given by Hooke's law. So F is spring force, x is displacement at the end of the spring, and k is going to be the spring constant. So the negative sign in the equation is because the force is always in the opposite direction from the displacement. So the potential energy stored in a spring is going to be U equals 1/2 kx squared. And then the period of a spring is going to be T equals 2 pi rad m over k. And so m is going to be your mass, and then k is going to be your coefficient. So then moving on to the spring is going to be 1 over F and 1 over T. So we just talked about this. You could do this either way. It just depends on the problem, which ones you guys want to use. And so then these two are going to be called the reciprocals of each other. Let's move on. So now I'm going to be passing it on to Tammy for Intro to Pendulums.
All right. So basically, if you look at this GIF right here, or GIF, whatever you say, right here, I just want to highlight the similarities between pendulums and like mass spring systems. They're basically the same thing. The only difference is that displacement from equilibrium for mass spring systems is linear, while for pendulums, it is an angular displacement, right? Because you can see that angle it forms as it moves past the equilibrium position. So, but obviously it's very similar. It's essentially the same thing. So at positions 1 and 3, velocity is 0 because the pendulum is changing direction. These are things that makes total sense. You can think about it and you'll get the answer, but it's nice if you could just like keep it in your head, right? So at positions 1 and 3, which is like the ends for both mass and mass spring systems as well as pendulums, velocity is 0, and acceleration is maximum at this point. It's also called amplitude. At position 2, that is our equilibrium position. Velocity is the max there, and acceleration is 0 because if we think about it, but based on Hooke's law, x or kx, the x is going to be 0, making F equals kx 0. So there's no force there, therefore it's not accelerating. Last point is for pendulums is we always want to make sure the angle for amplitude is less than 15. If it's greater than 15, where that we can say that that pendulum is not in simple harmonic motion. I haven't seen a question like that, but it's good to keep that in mind. Okay, passing it back to Anastasia for one more slide.
All right, so now we're going to be going over pendulums. So the period of a pendulum is going to be given by the equation T equals 2 pi rad L over G. So G is always going to be your gravity, which is going to be negative 9.8, and then L is going to be your length. And also the thing about G is that it doesn't always have to be negative 9.8 actually. Sometimes you can like have different different gravity values depending on the problem, like if it's on another planet and stuff. So the pendulum is going to be a lever that is suspended from a point such that it can swing back and forth. And as the pendulum swings, its gravity and tension remains constant. So the potential energy of a pendulum is the gravitational potential energy of the pendulum's center of mass at its max displacement. So velocity of a pendulum can be calculated using the conservation of energy. Next slide, please. Multiple choice practice. I'm going to be handing it over to Tammy.
Okay, guys, so we have some more MC right now. And so yeah, we can go over it. I promise that these are more straightforward. It's still a little conceptual, not as conceptual, I guess, as the previous ones. So yeah, let's talk about these. So we have 5 total. Let's start with the first one. The first question is, a particle oscillates with simple harmonic motion with no damping. In my mind, I'm thinking no damping means no friction. Which one of the following statements about the acceleration of the accelerating particle is true? A, it has a value of 10 meters per second when the oscillation is vertical. B, it is 0 at the instant the speed is at its minimum. And C, it is 0 at the instant the speed is the maximum. There's a poll, so please answer in that. Yes, actually, it's just something oscillating. It doesn't have to be a pendulum. Or I guess it's suspended, yeah, in air. Okay. All right. Let's move to the, I think everybody got a chance to answer. Okay, it's not being. Okay, guys, here is my work for this problem. At equilibrium, the only force acting on it is the spring force because it is vertical. And we can just use Hooke's law here, which is spring force is equal to K constant times X. We can equate our force, spring force to MA, again, because spring force is the only net force acting on our system here. And MA is equal to 0 when it is at the maximum. Or the spring force is equal to 0 at the instant when the speed is at the maximum. Therefore, we can say that acceleration is equal to 0. Lily, I guess you're right, because we're talking about a vertical system here, not a horizontal. Again, let me say this, that the springs and simple harmonic stuff, it does not have a uniformly accelerate a uniform acceleration, which is why we can't use the UAM equations. So the acceleration is not uniform throughout. For sure. I can repeat that. So the answer is, at equilibrium, the only force acting on the system is spring force, right? Yes, the correct answer is C. Yeah. But just in case anybody else wants to hear, the speed is max at equilibrium is correct. Yeah. And our net force is spring force. And so we can equate that to MA. And because our spring force is 0 at that point, acceleration is equal to 0. Suhas, it's vertical. So we're not going to be considering horizontal component. Good question. How do you know that this was a spring rather than a pendulum? It talks about it. Particle oscillate. Oh. Yeah, I should have written that in the problem. We can assume that it's vertical. Yeah. All right. Okay. So let's move to the next problem. It's a little bit more mathy, I think. Next slide. Yes. Okay, this is with real numbers for once. So we're given a 2-meter pendulum on a particular planet, has a period 4.2 seconds. What is the gravitational field strength on that planet? You should be able to solve this one. So take a minute, and when you're ready, please put in the chat. All right. I'm seeing a lot of C's in the chat. Yes. Okay. I think we all agree on this one. Nevertheless, let's go through it. Let's go to the next transition. Very nice. Yes. So we know our pendulum period equation, and that is just 2 pi times square root of the length of the pendulum divided by the gravitational field. Now what we're trying to do is basically isolate G. While we do that, we remember we need to square everything to make to get G out of that square root. That's the reason for the why 2 pi became 4 pi square and why t became t square. And after that, it's just some plug and chug. Yeah, so for L, we're told that the length of the pendulum is 2 meters and the period is 4.2 seconds. And then that's squared. And then that's how we get that answer. Why are the units N, kg? Okay. Good question. Does any of the student hosts know why? Because I kind of just saw the options and I was like, okay, N, kg. I'm sure if you like break it down, yeah, newtons are kgm squared. Okay. I'm going to take Juliana's word for it. All right. Any other questions? The vertical. Oh, no, it's the other way around. Not sure what I said to confuse. But remember, or yeah, horizontal is like horizon, right? So horizontal is our spring mass system and vertical is like down. So that's a pendulum. Okay, are we ready to move on to our next question? See how the period and acceleration time. But where would meters from L go? There's more questions about the units, correct? The period is in seconds, and then L is in meters. That's meters per second squared. S squared is equal to M over S squared. I'm not too sure. Yeah, I mean, yeah. Is everybody looking at Juliana's chat right now? She's explaining it. Yeah. Yes. Ari, you're right. Yeah. Okay. All right. Let's let's move on to the next question. This one, maybe it's a little conceptual. So yeah, take your time. We have time. So. All right, I'm seeing a lot of B's. I actually saw a bunch of options. I saw C's and A's. Is that a okay? Yeah, I see D, C. Yeah. Okay. So, all right, let's pull up the solution. This is, yeah, I think you guys will like this one. Let's move to the next transition. Yes. So we have our period equation for mass spring systems, which is 2 pi square root m over k. All we're doing now is just plugging and chugging and seeing which one is the greatest, right? So option number 1, we have normal. So it's just m and k. So we plug that in and we get that as our option number 1. It's just 2 pi square root m over k. For 2, we see that we have 2m instead of m. So we just plug that in. Already I can see that the 2m period is greater than just the plain m because numerator increase the period, right? And next is the k value is 2 for option 3. And that is in our denominator. Denominator, whatever's in the denominator, it's going to make the period or whatever it's equal to decrease when you increase the denominator. And finally, option 4 gives us 2k and 2m. So you can see that right there. Basically, what happens is it just cancels out because both are 2, right? So yes, that is basically how we figured this out. So I can clearly see here that option 2 has the greatest period. And then that's followed by option 1, which just has normal. It looks exactly like our equation. And then 4 comes next. Oh, 4 and 1 are equal to each other. And 3 has the smallest period. Okay. Yep. All right. I don't see any questions. Please ask if you do have them, but I think we can move on to the next slide. Okay. Our question states when a 12 kg mass is Laura, the answer was option B. Do you want to see it? You can see it in the slides after, but okay. Yeah, okay. So I'm thinking, okay. So this is going to be our last MC before we get into our final FRQ. So yes, this is the question. When a 12 kg mass is suspended from a spring that has a spring constant 190 newtons per meter, and is attached to the ceiling, how far will the spring stretch when the weight is in a state of equilibrium? Okay, take a minute. Oh, and please vote in the poll. We have 15 votes for B. Okay. B. Okay, so let's go through it. I see a lot of B's, so that's good because that's the right answer. Let's move to the transitions. So we have our Hooke's formula, K times X displacement. We're just going to isolate the displacement because we're asked for how far will the spring stretch when the weight is in a state of equilibrium. And remember the horizontal forces acting on this mass is spring force and mg going downwards. They are equal to each other, so we can basically replace them. So for spring force is equal to mg. So we just replace or substitute the mg in for the spring force. And yeah, we have our little equation. Once we have our equation, all we need to do is plug and chug. We can do 12 times 10 over 190 to get 0.63 meters. Sorry, a little typo there. I meant 0.63, not 0.62. But yeah, I saw a lot of people in the chat saying basically the same thing. So great job. Great job. Okay, guys, this is the last MC and y'all made it. We'll definitely be going over more, and especially that particular MC that kind of got all of us tripped up. I will definitely be going over that tomorrow and breaking it down more. Good job.
All right, now we're going to be doing an FRQ. We're going to be doing an experimental design FRQ. So I know a lot of people are confused on that. So we're going to be starting off with that. So in this FRQ, the pendulum shown, it's in the bottom right corner. The pendulum shown above consists of a bob hanging from a light string. You wish to experimentally determine the frequency of the swinging pendulum. So we're gonna do each question one by one, and then we're gonna be reviewing answers after each one. So by checking the line next to each appropriate item on the list below, select the equipment that you would need to do the experiment. And you are going to be selecting one of the equipment pieces to try and determine the frequency of the swinging pendulum. So think about the equations that we talked about, and how that relates to time. So when you guys are done, let me know in the chat, and then we will review that answer. Yes, you're going to choose one. All right, so can we go on to the next slide, please? So the answer to it is going to be a stopwatch. And there may be other ways to be able to think about your experiment and like create one, but we're going to be using a stopwatch today. So can we go back to the FRQ so we can look at B now? All right, so for B, you're going to describe the experimental procedure that you would use. In your description, state the measurements you would make, how you would use the equipment to make them, and how you would determine the frequency from those measurements. So we're going to be doing an explanation for stopwatch, but as long as it makes sense and as long as it's a logical reasoning to why you would want to use a meter stick, additional masses protractor, you would get full credit. So it really just depends on how logical your explanation is. But the stopwatch is definitely the easiest one. All right, and then let me know when you guys are done doing B so we can look at the answer. You can use multiple if the question allows you to. Yes. Experimental design is definitely one of the more kind of like ones you have to really think about. Um, Most of the time they're just relating back to the equations, so you really just have to think about the equations, how like stopwatch is going to be your time, meter stick is going to be length, protractor is going to be your angle. So you can just really connect those back with the equations that we used. And you can form your experiment based on that. The first question is going to be asking you what equipment you would want to use to determine the frequency of the swinging pendulum. And then the second one is going to be the experimental procedure that you would use. Make sure that you state the types of measurement, how you would make the measurements, what type of measurements you would take, and how you would determine the frequency of those measurements. This question does imply select the equipment that you would need to do the experiment. So you can do multiple, it does not say just choose one, but for the sake of time, we're just going to be looking over one equipment today, which is stopwatch. But yes, you can choose multiple because it does imply it. All right, now can we move on to the next slide? So a sample answer, oh wait, can we go back to B? Yes. So for B, it's going to be, we're going to use a stopwatch to time the period of the bob. I would pull the bob up to some point and start the stopwatch at the moment I release the bob. Then start the timer once the bob swung over back to the same spot where I had released it. I would plug that time in seconds into the equation F equals 1 over T or T equals 1 over F. And you can find frequency in that way. So you can just really find any way you can measure frequency with the tools that it provides you. And as long as it's a logical response, then you can get full credit. So now we're going to go back to C. Can we go back to the FRQ, please? Yes. So for C, your next wish is to discover which parameters of a pendulum affect its frequency. So you're going to state one parameter that can be varied, describe how you would conduct the experiment, and indicate how you would analyze this data to show whether there is a dependence. So now we're going to be working on 3. Let me know when you guys are done. Think about what affects the frequency and also how it can be varied. And also you have to describe how you would conduct the experiment, and you would also have to indicate how you would analyze the data to show whether there's a dependence. So there's many things, many parts to a problem. So make sure you grab all those points up and try and explain every part of the problem every time you see one. All right, so let's now go over C. Since this is kind of lengthy, I will be showing you guys how to explain this correctly. Let's go to C. So I would vary the mass at the end of the same string by using the additional masses and the stopwatch. I would do a few trials with each mass using the same procedure to find frequency, timing how long the mass takes, how long or timing how long the mass takes to come back to the point where I release it. I would analyze the data by seeing if average frequencies, 1 over t or 1 over f, are equal or not. If frequencies are equal, pendulum's frequency does not depend on mass attached to the end of the string. So yes, the answer to this is going to be length. So one parameter of a pendulum in order to affect frequency is going to be your length. So pendulum with a longer string will have longer frequency, while a shorter frequency will have a shorter string will have higher frequency. So that's why you would want to take additional masses and our stopwatch. And then that's how you can this is one of the ways you can conduct the experiment. Do we have to use an experiment from part A to show? We have to use an item from part A to show how our experiment. You don't have to. It really just depends on if you give a good explanation. You don't have to use more or less or more or less items or equipment. No, but it does lengthen the pendulum. So since the length doesn't affect it, the length will get longer with additional masses. That's why we would use additional masses to lengthen the pendulum. All right, let's look at D. I think this will be the last one we're going to do. Back to the FRQ, please. There we go. So after swinging for a long time, the pendulum eventually comes to rest. Assume that the room is perfectly thermal insulated. How will the temperature of the room change while the pendulum comes to rest? So would it slightly increase? Would it decrease? Or would it have no effect? Or it would just remain the same? And also to remember to justify your answer. Think about energy, think about exchanges of energy. So thermal energy, mechanical energy. All right, I'm seeing a lot of good answers. Chloe, yes. You can say that. Yes, you do need to justify your answer. All right, let me know if you guys are ready to move on. Yeah, always make sure to read the whole problem. If it says justify it because you'll be losing points. And that can be a really big chunk of points. Like even justifying it can be like 2 points. So always make sure to read it and justify it. All right, let's move on to D now. The answer. There we go. Yes, it would slightly increase until you'd have to write your justification, which is the pendulum transferred heat to the environment because not all energy is conserved. And so the potential energy at its max height and kinetic height at lowest point. So the energy loss is going to be released as heat to its environment. There's many different ways. There's honestly a few different ways you can explain this. So like less mechanical energy gets converted to thermal energy. You can talk about potential energy, kinetic energy, and such. So this is going to be our last FRQ for part to this FRQ that we're going to be going through. And for E, we are going to be covering that on night 5. Also, please make sure to take the night 3 survey. It is linked in the crowdcast, so please make sure to take it. And we will be seeing you guys tomorrow. Thank you guys so much for coming.